Greetings. It is clear that bubble sorting two subarrays of half the elements is much faster than sorting the whole array. But the sorting is not done. The two must be merged. Could that consume half of the time? We'll find out. First, let's take a look at merging the two subarrays. The process is as follows. First, we copy all the elements into an auxiliary array. And that's one of the drawbacks of Mergesort. It requires twice the memory. We have to have an auxiliary array. Then we copy the elements back into the original array, alternating between the subarrays as necessary to produce a whole sorted array. To do this, we maintain three indexes. K is an index that indicates where we are in constructing the sorted array. I and J are indexes that point to the lowest elements ready to be copied from the two subarrays. In this diagram, Ann and Aaron are the first candidates for the first slot in our combined array. Aaron comes before Ann, and we copy it and update the indices K and J. Next, we decide between Ann and Beth, and Ann is selected, and we update the indices K and I. Beth is before David, we update K and J. Next, we consider Carl and David, and Carl is before, and we update K and J. Now David is before Ed, we update K and I. Ed comes before Fiona, we update K and J. Now that J points past the last element in the second subarray, we do not have to consider any more items from that half of the array and just copy the rest of the items from the other subarray. And this is of course done in a loop. So these point indexes will be incremented as needed. And here we have the sorted array merged from two subarrays. Here is a function that does the merge, and the indexes used here are the same as in the diagram that we had. So we have K pointing to the merged array, and then I and J are indexes into the subarrays. We can see it here. But we start by copying the whole array, to be merged into the auxiliary array, and then we copy from the auxiliary array into the original array, copy from either the K or the J indexes into the subarrays. Here's the code for it, and I try to clear it up with some comments here. We start by checking for the condition of if we have finished all the items from either of the arrays, then we automatically use the other array which has any items left. But otherwise we do the comparison here between the two and select accordingly, either J or I, whichever is next in the line. If we take a look at the interface for this function, it's a template function just like before. So we're talking about items here. That should not be new for you, and the function expects the array. This is the array with that contains both the subarrays and will contain the merged array afterwards. Then we need an equally large auxiliary array that is just used as a temporary storage. and the caller provides this to the function. And then we have 3 indexes into the original array. It's the first item, the middle where we split the array up, and the last item, last index into the array. And then we derive the I and j indexes here, and yes, and the code follows. Now let's take a look at the main program. Here I've added the auxiliary array. Just created another array here for use in the merging process, and the rest of the code has not been changed right now. We have we bubble sorted the lower part of the array here, and then we bubble sorted the higher part right here. And now we want to see. Now we want to merge them together, and we provide the original array called A, the auxiliary array called aux, and then it expects to get the next parameter here is the low point. That's just item number 0, first element in our array. The middle point is n divided by 2, and the upper element is n minus 1, because our array is 0 indexed, ranging from 0 to element number 999, which is n minus 1. Okay. Then all we have to do now is, it will be interesting to see how fast this merging process is. So we will provide another timer here, restart the timer here, and print out the result right here. Okay, good. And I'm gonna place a breakpoint here so we can examine the array and see if it's really sorted. Okay, that was quick. Let's take a look. Yes, first half less than second, second half less than second, and the merging does not consume the time that is saved. It was 4 seconds total sorting the whole array. It only consumes a tiny fraction of that time. So this is what we have to do, added work, since we have sorted it in 2 subarrays. But combined, this is less than 2 seconds compared to over 4 seconds. And the only thing left to do is to check if the array is actually sorted. And here we can see the beginning, and scrolling here through, we're up to 300. Here we are at the 500 point, that's the middle, and we can see it smoothly continues here in a sorted order, all the way up to element number 1000. Now the question remains from our earlier video: would we gain more speed by breaking these arrays again up to smaller subarrays and sorting them separately and merging them later? And for that I'm gonna stop using this manual splitting of the arrays and just go directly to the Mighty Mergesort algorithm. So here we are with the Mighty Mergesort, and look at this code, only a few lines. Now the interface for this function is similar to the merge function. We need the original array, we need an auxiliary array for the merging process, and we need the beginning of the array we want to sort and the end of the array we want to sort. There is no midpoint here, it's calculated later in the code. So at one point in our divide and conquer video, we wondered, or I wondered, if how often can we gain something by splitting up the array? Is there some overhead involved? Should we stop at 10 elements or something? There may be, but still, the classical merge sort algorithm continues splitting up the array until this condition here comes. That is, we are trying to split up a subarray of one element. So there is nothing more to do. Then we return. But apart from that exit condition, we calculate the middle of the array that is being sorted. In the beginning, we have here 0 and 999. So we calculate the middle of that, and then we sort the lower part from low to the middle point, and then we call again sorting the upper part from the middle plus 1 to the high point. And this means that we will be splitting up the lower part of the array again until we get into this exit condition here. Then we return and start splitting up the upper part of the array again and again until there is just one element that we are trying to split. And when that is done, we have a large call stack of where we will be returning and merging increasingly larger subarrays until we stand up with the fully sorted array. That's the Mighty Mergesort. That's a beautiful algorithm. And now let's go ahead and change our main program to use this Mighty Mergesort instead of this the bubble sort. I've already done that here. I've just plugged it in here, Mighty Mergesort, the array, original array where we read in the 1000 records. I provide the auxiliary array for the merging process, and the initial condition, which is to sort the array from the first element, index 0, to the 1000 element, which is index 999. And then there is nothing left but first to time it. Let's go ahead and run this and time how fast it will go, and it's done. 65 milliseconds. 65 milliseconds from over 4000. So that's quite some gain here. And let's maybe we should go ahead and take a look and see if the array is actually sorted. It's not enough just to be fast, it also has to work. So let's take a look. Here we go. Start with April, and we can go through the whole array here. We are approximately at 500 here, and we're down to K. We continue until last element. So the whole array sorted in 65 milliseconds. That's the Mighty Mergesort. Thank you for watching.